All right. Thank you, Luca and Ariel, for organizing this workshop and inviting me to present the works that Guy and I have been doing for some time now. This is works that we have not published yet. So, okay, I'll give you an overview of what I want to address in this 25 minutes that I have. Firstly, because we have all been hearing about Axion cosmology so far, I don't need to go through an introductory phase where I explain to you what it is, but I will quickly review all of the stuff in order to be complete. I'll also talk about review some of the earlier work done by Guy and Moore-Klaer, specifically the two scalar effective models that they came up with to simulate high tension strings, string networks. And then we'll move on to recent work on the spectral analysis of such high tension string networks, and we'll present some preliminary results. But I must put a disclaimer that this is still unpublished work, and more details will follow later in an upcoming paper. So take whatever I say with this grain of salt, because not everything is like polished right now. But yeah, we can talk about Axion cosmology quickly. So all of this, as all of you know, this starts with the strong CP problem, which is the fact that the strong sector does not have a theta angle observation. It's observationally consistent with being zero. So the question is, why is it zero? Is there a reason for it other than saying that it is just a coincidence? So the solution that Patrick Quinn came up with was that, okay, let's introduce one more symmetry to the theory. Let's introduce an anomalous U1 global symmetry. And, after that, you introduce it with a Mexican hat potential that has a valley which constitutes the vacuum manifold, and as the universe cools down, the symmetry spontaneously breaks, and every point in space-time picks up a certain phase in this vacuum. And as most of us are already comfortable with the idea of having, or we are more inclined to think that it's happening after inflation, and that's what we also assume. And once the universe picks up a phase in every point in space-time, Hubble mechanism ensures that in causally uncorrelated layers, the assignment of the phase ensures that there are some certain topological defects, such as strings emerging, and the strings are initially separated by distances proportional to the Hubble distance. And later on, during the QCD crossover, instantons come into play and explicitly break this symmetry and give a mass term to the axion, which is why it's not a Goldstone wave, but a pseudo Goldstone wave. And as it tells the potential, there's a new bottom of the potential, a new preferred phase where the axion oscillates into and settles down. So that's a dynamical picture of how the axion, being the dynamical version of the QCD triangle, how it is fading to zero. And since the axion gets a mass, it's also dark matter, and which is why all of us are so interested in this thing. So here is the Lagrangian to remind you. The Lagrangian contains this is the Mexican head potential, and this is the contribution due to instantons. This is the thing that tilts the potential. Initially, this thing is negligible, and you have a proper vacuum manifold, but as the universe cools down and the PCD crossover, the potential tilts and the axion starts to oscillate down to a mean. So here, Fa is the decay constant. Lambda is related to these mass of the radial excitation, which is also sometimes called the axion. And this is the topological susceptibility at temperature T. And if you just expand the cosine here, you can find out what the mass term looks like for the argument of this complex scalar, which is what we call the axion. Hence, we find that the axion is related to the susceptibility and the decay constant. The decay constant is fixed by cosmological arguments. It can be derived, and the simulations tell you. So, if your simulations give you the axion number, which goes like K squared H star, the Hubble's constant at the time the tilting starts, and there is some factor K which comes from simulation, and then this thing will finally determine Fa, and this can determine. So the previous work that has been done in our group has entirely focused on determining K, and therefore finally determining action for the mass of the axion. Right. So a quick reminder about the topological defects. The axions, axion strings are objects around which the axion phase goes by a total of 2 pi. That changes by a total of 2 pi. So it means that if you were to continue towards the center of this path, then there should be a place at the core where the axion moves to the vacuum manifold. So it's no longer an axion. You will complete the theory. And that is the string, and strings exist until the potential starts to tilt. Once the potential starts to tilt, there is a preferred phase in one direction, and the other direction you have a region where it is high in energy, so it makes up the domain wall. The domain wall pulls the strings together and tries to annihilate the network, and the annihilation of the network is quickened, and soon there are no strings left at the end of the simulation. The tension of the string is proportional to the logarithm of the hierarchy of scales. MR inverse is the size of the core of the string, and H inverse is the size of the Hubble scale. So this gives you the hierarchy of scales, and it is quite large for the kind of simulations that can be done directly. So it can't be done. So, but our group has done before is come up with a model, hybrid model which is able to simulate very highly tensile string networks. So this model constitutes of two complex scalars and one gauge field. And this is the Lagrangian that defines the model. There are two rotation symmetries, namely rotation of the two complex scalar fields, and the two complex scalar fields have charges Q1 and Q2. So this theory exhibits a long-range light degree of freedom, which is this combination Q2 theta 1 minus Q1 theta 2. This is identified as the axion. And then there is another combination, which is Q1 theta 1 plus Q2 theta 2, which is gauged. And this model emulates strings with thin cores with very high tension, and the tension we can reach is now comparable to the physical tensions that we expect in QCD Axion string networks, and it also has the correct string field inversions. All right. Now, in our recent work, what we have done is try to study the spectrum of the Axion string network. The spectrum we have tried to we have defined it in different manners to see which definitions probably give a closer depiction of what really goes on. So we have some unfortunate nomenclature that may not make sense to everybody here, but I'll show you what we exactly mean by these terms such as bare, A dot, bread, by looking at what we exactly simulate. First of all, let me write it here. So, if you write down the expression for the axial number, we can write it as A dot squared K plus
If you are writing, we cannot see anything.
I'm sorry. Let me see what went on. Are you able to see now?
Yes.
Okay. So basically what we do is we have this quantity Ek, which is nothing but square root of K squared plus M squared. And usually we define the axial number using A dot squared, a contribution coming from A dot squared over Ek, another contribution coming from A of K squared. But this quantity is not well defined until very late in the simulation. So we thought maybe a better way of doing it is probably just looking at the gradients. So this is an equivalent way to find the spectrum or the Axion number. And since the energy, we can expect the energy to be roughly divided equally between these two components, we can also compute the Axion number or the spectrum from just one of these. Usually A dot is a better measure of the spectrum or the Axion number. But for comparison, we also compute the Brett version, the Axion square version, and bare means the one that is with the Axion squared version and the A dot version together. All right. Using this, we compute the Axion number as well as the spectrum. So let's look at some of the computed stuff. Oh, before that, I also should tell you what volumes we simulate. So for completion's sake, we also simulate 512 cubed, but we think the physics is wrong in 512 cubed because it is too small and we see some artifacts which are not physical. We also do 1024 cubed, 2048 cubed, 2560 cubed and 4096 cubed. When we say we say 2048 cubed is not exactly 2048 cubed because we have to worry about the number of pores there are in the, etc. So it's roughly say 2048 squared times 2304, and 2560 cubed is like 2560 squared times 3072. And 4096 cubed is more like 4096 squared times 4032. Now we, in principle, we could go higher, but we ran into limitations of compute hours that we had, so we could not simulate any higher. But our code is able to handle this, thanks to some. Thanks to, first of all, Intel's MKL FFT libraries from 2023, version 2023 onwards, because we had to also address a bug that was in MKL FFT before that, which prevented simulations beyond 2048 to 2563. But after speaking with Intel, people working at Intel and having this fixed from 2023 version onwards, we can simulate higher lattices. Other than that, we also simulate. We have to take some limits, which is the limit of MR T star going to infinity and MRA going to 0. So we do a series of, we take a series of values starting from 1.0, we get to 0.7, 0.5, we'll go up to 0.4. This is the lattice spacing, and this is the heavy scale. The upper one is the heavy scale limit, which will go from 400 up to, I think, 800 or so. And we find that our, we'll show you what we find with this limits. So first we calculate the misalignment Axion number density because we will divide by it and everything else. that we complete to find the production efficiency. And here's a comparison of what we get with Bayer and A dot. So it's bit. So red one is A dot. So there is some superfluous fluctuation here in A dot. Anyway, this is what we get. And if we compute the Axion production efficiency, which is the Axion number divided by the Axion number from misalignment, we get this. So this huge thing here is something we don't fully understand. This is the computation coming from the gradient version of the spectrum, where we don't compute it from Axion squared, but the gradient of Axion squared. However, in the end, they all agree. So this thing is all right. This is red. This thing is there. So there is red. Red, and A dot is just squared, scaled appropriately, and this is red AK squared over plus. All right.
There's a question from Javier.
Yes.
Just a comment. So I
All
think
right.
that this peak comes from the domain walls. So when you are calculating the gradients of the Axion field, and they have large contributions from the domain walls that drive the cosmic strings to destruction. And I think when they are all gone around time 4, then of course you don't have this contribution. So this, I think that's the thing.
Yes, that's true. But also we are not entirely sure why there is so much disagreement earlier in the simulation. We naively did not expect it to be so different, but that's what we found. We thought this this way of doing it might give a reliable answer before, but it doesn't. Moving on. So if this is the MRT star going to infinity limit, and we see that they agree to within their error bars to an incredible degree of accuracy. Right. And now this is the spectrum. So I plotted for now just the spectrum at MRA equals 0.4 and MRT star equals 400. And the blue one is at the start of the simulation, and this one is at the end of the simulation. So I don't know how some of you guys show movies in your slides, but when I do the movie version of this, what happens is this thing evolves, but somewhere in between it goes like this, and then finally it settles to this form. Now we can compare what happens when we have, say, MR equals 0.5, how it shifts. All right. So this was the start and end for 0.4. And the next two are the start and end for 0.5.
1 minute left.
All right, sorry, I am almost done.
Mhm.
And yeah, finally, the lattice spacing dependence through which we do our final extrapolation, and I don't want to give you a result right now. We will find it when we publish the paper. So since I don't have any more time left, I'll finish it here. Thank you for your attention. Yeah, thank you for the opportunity. If there's any questions, I will be happy to answer if I can.
Yeah, thanks. Okay. Questions? You can raise your hand using the reaction button. Otherwise, I would like to know a bit about the timeline, like when you expect to have results wrapped up in a paper, and what do you expect from the results?
I think we will. I don't like to give up the date, but I think in 1 or 2 months we should be together.
And what do you expect to have in addition to what you already presented?
So an extrapolation and like the changes. I did not highlight one of the changes that we made in the calculations. That in the previous work we had our simulations were based on purely radiation-based assumption, but we have made some corrections to that, so it's not purely radiation-based anymore. And we do this careful extrapolation, and we a better prediction of the axion mass. So that should be there in paper that is